Hello students. In this video we're going to transform this PDE, which looks like the heat equation, but there's this loss term here, this minus beta U. We're going to transform that into the good old heat equation here with no loss. And the reason we're going to do that is because this one here on the right, you know how to solve that using separation of variables. Okay? So first let me just show you how to make that transformation. And it's going to seem like this is coming out of the blue, but I'll be able to explain this away in a moment. Okay, so here we're just going to let u equal the exponential e to the minus beta t times w. Now, you may look at that and say, oh, that's e to the minus beta t. Well, there's a minus beta right there. So if this is a temperature, well, we remember this one here. This was temperature gain or loss dependent upon diffusion. Here, this looks like a temperature loss, and that makes sense if we have a decaying exponential. So then this W term must account for the diffusion part of it, and the e to the minus beta t must account for the loss. Okay, I'll explain it a little more rigorously in a moment. First, let's just see why this works to transform this PDE into this PDE. So we take the derivative with respect to t. Here we just use the product rule. That's what we did here in this step. So we took the derivative of the first term, second term left alone, plus the first term left alone times the derivative of the second term. Now the e to the minus beta t has no spatial dependence, so the derivatives just work out this way. Uxx is the same as wxx. And now we substitute that into the PDE. So just take a quick look and make sure that that is done properly. So we have the ut term here, we have the uxx term here, and here we just put in the u. And now we just do some cancellation. We see on the left-hand side and the right-hand side, we can cancel those terms out. That leaves us with just this PDE here with the exponential on each side, and there we can just cancel out the exponential. A lot of times when we do these transformations, we don't even write the exponentials, knowing full well that in advance they're going to cancel. But anyhow, we get this diff EQ as required. Okay, well the question is, why does this work? All right, well consider this initial boundary value problem where we have insulated boundary conditions. We have, or not insulated, I'm sorry. These are not insulated boundary conditions. These are fixed boundary conditions. In fact, we're going to see that this is not insulated at all because of this loss term. Okay, so these are fixed boundary conditions. Now, if you have heat diffusion inside of the rod, that's taking you to the boundaries, right? So remember that if the rod was hot in the center, then the diffusion is going to cool the rod down and get it to be a steady state of 0 because of the boundaries. Now, what you have going on here with the minus beta u is you have heat loss, lateral heat loss, so the rod is uninsulated. So you have heat diffusion in a rod accounted for by the duxx term, and you have lateral loss, heat loss due to the minus beta u term. So if there's, let's first just assume that there's no diffusion. Okay, let's simplify this a little bit. Then the PDE will look like ut, and then for any given x, x naught, we're just going to have this PDE here. So it's going to look like this PDE here, ut equals beta u, or minus beta u, right? So let me put a minus sign in there. Okay, now we're going to solve this ODE as an ODE, and we're just going to view it as du dt equals minus beta u, and well, of course, that means that u is equal to e to the minus beta t. So u is the non-insulated temperature, and we have this loss due to the minus beta u term, which is accounted for by the e to the minus beta t. And we could think of W as like the insulated temperature, okay, or the temperature that is just due to diffusion only, okay. So it's just going to match. It's just going to go to the steady state on the boundaries, and the non-insulated temperature is U, because we're going to have this lateral heat loss, which is accounted for by the e to the minus beta t term. And the boundary conditions are still going to be the same. So the bottom line here is that you can take this PDE using this transformation here, which accounts for your lateral heat loss, transform it into this PDE here, and then use these boundary conditions, which are the same because, um, of course, there's no spatial dependence on the e to the minus beta term. So u0 equals 0 means that you can cancel this term out and you'll still get w0, and similarly for u1 and w1. And then if you plug in t as 0, e to the 0 is 1, so ux0 is the same as wx0, and that'll still be f of x. So once you have this PDE, you simply apply these boundary conditions. You solve for w, and then you transform back for w for u using this transformation after you have w, and that is your solution. Okay, let's take a quick look at what this is going to look like. So if I have a heat solver here, so here's our fixed boundary conditions of 0, and we have some heat diffusing outward. Remember, this was concave down, so that means that uxx is negative, so that means that the ut is going to be decreasing. So we had some heat loss here, and it's diffusing to the boundaries. I just stopped it there, but notice that, it's whatever. It's here's the peak, and it's about like 0.8 to 0.9. Now that's for just regular old heat equation. Let's let's do the same experiment again, but this time let's add the loss. Okay, so you can see it's diffusing, and it looks like it's moving a little bit faster. And here I had 0 boundary conditions, but I had some heat loss in the center, and you can see that it looks like it's a little bit closer to 0.5. So let's just compare that to the regular old heat equation, and you can see that with the loss, with the minus beta u term here on the right, we had more heat loss than we had when we just had ut equals duxx. Okay, so that minus beta u term, resulted in more loss, and of course you'd expect that with an uninsulated rod, and it's really the other way around. You're using the equation to model the fact that you have an uninsulated rod. Okay, that's all I have to say for this problem. I'll leave this up, and good luck.